Welcome to AI-driven perception, learning and mapping for drones. This lecture talks about foundation of neural networks, basic concepts. We talk about types of learning. When we talk about types of learning, supervised learning, we are learning with teacher, right? So you have a labeled data. Every data corresponds to a specific label. That label acts like a teacher. The feedback, there is a direct feedback. Feedback is nothing but the error, the prediction that what you have and the actual label data, the difference is used as the feedback signal. And predict or outcome for the future for unseen data, if you give this after learning, the knowledge extracted between the input and output used to predict the future outcome of the unseen data. If you look at learning without teacher, what we call unsupervised learning, where there is no teacher, there is no clear goal, there is no label or data, there is no feedback mechanism. It is like given a data, you find the hidden relationship or hidden cluster, a hidden group, right? Hidden knowledge in the data that we need to extract. There are certain scenarios where learning without teacher is there, but there is reward signal is available. It's not a direct feedback signal, but it's an indirect feedback signal. For example, if you complete the goal, you get a reward, right? So this is an indirect feedback. It doesn't say that is that the way to do the goal, right? For example, if you submit the assignments, you get the marks, but it doesn't say exactly how to do it, right? So the reward signal is an indirect feedback signal, helps us to find the hidden relationship, right? So this helps us to learn series of actions that we could have. There is another concept in learning called semi-supervised learning. Some has a label, some doesn't have a label, right? So we use the labels in the beginning to learn, and some of them is not labeled, which we will use our prediction to correct ourselves, to get the confidence in prediction. Now let's discuss in details about different types of learning. Okay, so when you look at supervised learning, we also call supervised learning as a inductive learning, right? So there is an environment, the environment sends a signal, right? That's my input signal. The same input signal is given to a teacher. The teacher looks at the signal and gives a label, right? Based on the input signal, you make the prediction and look at the difference between your prediction and the label provided by the teacher. That's an error signal represented in red color, which is used to update my weights which represent the knowledge. Let's say there is an data which I represented x. X is the input signal, right? And y is the label. x1, y1, xn, yn. So n observation set I have, and this will be used to train the network to find the hidden relationship between the input x and output y. Okay, so the network tried to emulate the teacher. Network tried to understand the relationship. So if you look at the neural network, it has input signal x and the weights which represent the knowledge. F of x comma w is used to predict the y. Right? Here it could be a prediction is like I can predict the temperature, or I can say whether the input x belongs to a specific class or not, which is what we call classification problems. The error signal is used to update my weight w. Okay? This is supervised learning. For example, I can use the supervised learning for a function approximation problem. Let x be the input, and what you see here is on y-axis, which goes from 0 to 3, is my output, right? So for x, this is how our output varies. I can approximate this signal, or I can have a two-class classification problem. What I mean, I have set of samples. Red color is one group, green color is another group. It's been labeled, all these green one belongs to class 0, red one belongs to class 1. What's my objective? Objective is to find the decision boundary which separate these two into two different categories. So I use the feedback signal from the teacher to say this class 1 and class 2. My objective is to find the decision boundary which segregate them. On the other hand, if you look at unsupervised learning, there is an environment which gives a signal to the neural network. Okay? There is no teacher here. There is no teacher looking at what is the hidden relationship which we are finding. Right? So x1, x2, x3, xn, these are observations which I am getting from the environment. That is an input to the data. So how do I learn? I can use a competitive learning here, right? Because there is no error here. Error means the teacher says, oh, your prediction is right, your prediction is wrong, so I get the direct feedback. So I can always use a competitive learning, which is winners take all. If the sample X is similar to the previous sample, then I say these two are similar. Otherwise, it's a different sample, right? So I can always use the concept of competitive learning to learn the hidden relationship to find a pattern in the data, right? So what is my objective here? Learn is task dependent measure. For example, how the data quality, right? I can just look at the measure of the quality of representation, right? So I can just use that also as a feedback signal. Typical example, clustering is a typical example. I am trying to find similar samples. If samples are similar, I put them into a single group, right? So if the sample is different, I put them into a different group. Say for example, there is a two-dimensional data x1 and x2. I am trying to find the group and say there are 4 clusters exist here, and this all yellow belongs to one group, and this is another group, dark green is one more group, light green is a different group, and purple is in another group. So I am trying to find hidden group present in the data without direct feedback. We talk about a reinforcement signal. It's a typical, I am just showing as an example with an actor and critic, right? There is an environment which goes to actor network, right? And the same environment signal goes to a critic networks. A critic gives me a feedback and say this is what I am expecting as a goal. And based on that, you provide action into the environment. This changes the environment, and that gives an input signal, and this signal goes to actor network. So there is a kind of a reinforcement based on the reward signal which goes to the system, right? So what we talk about, learn the input-out mapping through continual interaction with the environment. So here I just show a typical actor-critic network. There is a reward-driven approach. For every action, there is a reward signal, and I use the reward signal to choose what action that I should perform in the environment which maximize the benefit. The goal is to optimize the cumulative cost of action. What will happen every time I just make an action in the environment? What is the cumulative? It's a typical example. I start from a home. I want to reach at my destination. If you reach your destination, then you get a reward. If you reach your destination faster, you get a better reward, right? So a typical example is that if you are looking at a drone starting from one location to reach the goal, right? It has to reach the goal first. Second is it has to reach the goal faster. Very important thing is in the whole process, you should not collide with anything, right? If it collides, there is a damage, physical damage to it, right? So you can give a negative reward. So the purpose is we are training the drone to reach the destination so that it gets a reward without collision, right? So it learns the policy. Basically trying to control the policy. Again, you can just talk about aggressive maneuvers, non-aggressive maneuvers. Each and everything can have different reward signal. The whole problem here is how do you provide a reward signal, right? In a reaching goal kind of a scenario, unless you reach the goal, you don't get the reward. If there is no reward in the whole temporal process, it is also very difficult for us to learn. It's a very interesting topic as such, right? There are a lot of applications. We can talk about decision control, we can talk about obstacle avoidance problem, we can talk about predictive motion planning problem. All comes under reinforcement learning. When there is a swarm of drones working together to achieve the major objective, right? The mission to be satisfied or quench the fire. Now the question is, who are going to form a team, and how the team going to work together to quench the fire faster, right? So team formation is also a problem, and among the team members, how they allocate the load in such a way that they can quench the fire much faster also, right. So more like a decisions that they have to perform, and all these problems can be casted in reinforcement learning. Okay, very important aspect. To learn, we need data. Data is the key, right. The biggest problem is data is drawn from some distribution. Unfortunately, we don't know the true distribution. For example, if you want to learn to identify an apple, right, apple can be red color, green color, right, pink color also. Now the problem is we don't even know the true distribution of this. It can be small, it can be big, the shape can keep changing, right. So we don't know the true distribution. The challenge comes in the training data is drawn from this distribution, which is unknown. There is an unknown relationship between input and output exists. We sample randomly from this distributional space and take some data, right. Let us say these are smiley faces or the sample data which I am taking to learn the relationship between input and output. So what we are trying to do? We are train and test data are independently drawn from the distribution. So what we have the smiley faces. With that there is an unknown relationship. Let us assume it's a linear relationship between the data, right. I assume that the samples is single dimension space just for the sake of argument, right. X1, right, Y1. So I am assuming that there is a linear relationship exists, and the true parameters are beta naught and beta 1. What I do? I take a sample data and I randomly sample it. Those are the points that I take and I build my relationship. I build a relationship which is B naught plus B1x plus epsilon. Epsilon is my error. No matter what you try to fit, there will be always an error, right. So that is error that we are talking of, and now this relationship represent the data what we are looking at, right. Now there are lots of challenge finding this beta naught and beta 1. See, the original data, if you look at, it's when you sample it from the distribution. First problem is we don't know the true distribution. For example, if you look at apple and orange, if you are trying to differentiate and you are going to collect data, how do you sample the data if you don't know the true distribution which is required to separate between them, right. And this distribution sometimes can be skewed. So when you have a original data which is not centered, then what might happen is the slope or the behavior of the learning at different points will be different. That could leads to convergence, slow convergence problems. We may use a nonlinear function as an activation function. Those nonlinear function characteristics also impose certain requirement, right. Those requirements also will get influenced a lot in convergence process. There is a relationship between data and the activation function which we are going to use. So typically we look for data to be centered. Think about it now. I am taking age and salary. Age maximum, we can just think about approximate age is about 85, let us assume, lifespan. Okay. We have some outliers will be there beyond that, right. But salary, if you ask, average salary can just go from typically from 10,000 all the way to 1 crore, 10 crore also. So if you look at these data, it is not going to be really balanced, right. So we may have to center the data, we have to normalize it so that we are giving equal importance to age as well as the salary, right. So we may have to normalize. We will discuss all this in much more detail once we started introducing the learning process and activation functions, how activation functions influence together in terms of convergence with respect to data, right. So just think about it. There is an unknown distribution from where we are taking a data. The sample data that what we are taking may not represent the entire distribution. That itself is the first problem. The second problem, whatever we sample, the original data is not going to be perfectly zero-centered and normalized, right? So that is also going to affect my learnability, right? Learn to find the relationship as close as possible. So you have to do normalization, which will help in learning. So it will help the activation functions. Most of the activation functions are symmetric, right? We'll talk about it in next lecture when we start introducing nonlinear activation functions. At that time we'll appreciate why I'm saying symmetric, why the gradients has to be smoother, why we should avoid saturation, because we talk about nonlinear function, it can saturate at a different point. And if all the samples goes and falls on those regions, you don't get variations for an input. You don't get a variations for input, you will not be able to learn more efficiently. We will discuss in more details in subsequent lectures, right? At this point of time, what you need to understand, data preparation is also very important. So let's look at different applications of these networks, right? Let's talk about healthcare application. Deep learning has been widely used in healthcare. It's used in drug discovery. It is also used modeling protein ligand interactions, predicting blind affinities, generating novel molecular structures also, right? Not just that, it's been used, convolution neural network with a graph also has been used to predict compound libraries. If you look at MRI data, people use MRI data to predict the activities, to try to decode how human brain thinks for certain activities. So they call it activity based MRI. Sometimes they just do functional MRI to understand. Sometimes they resting state MRI signal to find out residual memories. People try to echocardiogram imaging to understand the functions of heart. So ultrasound images to understand. So if you look at it, use of AI in various fields, right? For a wide variety of applications, AI has been used significantly and the impacts are quite significant, right? Now if you look at further in healthcare itself, people started using recurrent neural network to design molecules of optimal pharmacokinetic properties to understand that. They also used to analyze the medical images to diagnose patients or accurately identifying the cancer cells, right? So the use of AI ranges from design and understanding of properties of a different molecules to diagnosis. Now we look at an engineering application which is more relevant. I can keep talking about precision agriculture and so on and so forth, but I don't want to do it. Let's get into the lecture immediately. What we are interested in. We are interested in how AI is going to play a role in drone, right? And robotics. I can use the AI significantly for autonomous driving, right? Autonomous operations, right? So moment I say autonomy, decision making ability is required. The drone need to learn to make decisions based on its observation or measurements, right? That's the key aspects of it. You can also use for design optimization. For example, if I'm just trying to do what's the best configuration that I could have, right? Can I have a neural network to design the wing of the drone such that I can have a maximum endurance, I can have a minimum fuel consumption, or I can have minimum signature, right? So we can look at unconventional shapes evolving, and we have to look at, of course, once is the design, second question we need to talk about it, realization capability, manufacturability, the performance evaluation. We have to evaluate all those aspects of it. I'm just trying to give you a philosophical understanding where people are using it significantly. They are using AI to design optimization. They are also using neural networks like CNN. They develop 3D deep neural networks to solve computer vision techniques to get perception problems. They also use reconstruction problems, which we saw in our motivation lectures, right? Now all these are fine. We have talked about neural network, we have talked about history, we talked about types of learning, we talked about two foundational tasks. The problem is either is classification problem or segmentation problem or prediction problem. How do we evaluate the performance? We need some metric, right? So in case of regression, and we assume this ground truth is there, right? Y is the label. I am assuming the ground truth is not biased, right? It's accurate. So what we want, the neural network to learn the relationship between the input and output, and it makes a prediction. Now I need to know how good is the prediction. I have the error signal EI, which is nothing but the ground truth minus prediction, right? I can use mean square error over the n observations that I have. What's my squared error? Mean squared error is measure, or I can use root mean square error, right, to understand how good my prediction is. I can also use a measure called R2 or R square we call. R square score measure how much the variance in the target is explained by the model, right. Let us say mean of the ground truth is y bar, right. We just compute like 1 over n, sum of I is equal to 1 to n yi. Then we compute the residual sum square, basically the error square. Yi is the ground truth, yi hat is a prediction, the residual is yi minus yi hat, the square of it, right, the sum square of it. We compute that, and we also compute the total sum square if the y is the with respect to mean value, right. What is the ground truth? What is the mean value of the signal? And that is what we call total sum square. Now from there we find out the ratio 1 minus SSRES, basically how much is the residual sum divided by the total sum square, the ratio with 1 minus the ratio. If it is closer to 1, which means the prediction is as accurate as possible, right. We have to achieve the prediction such that R2 is closer to 1. Now when it comes to classification problem, we have different metrics for classification problem. We talk about accuracy, right, how accurate you are. What is my classification problem? I am given an observation, I am asking a question whether it is an apple or orange. The ground truth says it is an apple. If you predict an apple, then I say you are correct. If you say orange, you are misclassified. So overall accuracy, it kind of measures the proportion of correctly predicted samples out of all the samples, right. Accuracy is number of predicted prediction divided by total number of prediction. Usually accuracies we express in percentage, right, which means we just multiply by into 100. That gives a percentage accuracy, right. Now if I want to put it in mathematical sense, right, if yi is equal to yi hat, right, it is more like if these are same, then your prediction is 1, if it is different it is 0, right. So I am just trying to find out how many predictions where the ground truth and the predictions are same, right. I can measure that. That is the overall accuracy, right. But then we have to understand little deeper, right. For an instance, when a model correctly predicts the presence of a condition or the positive class, right. For example, when there is a wildfire detection, sensor triggers an alarm where there is an actual fire in the forest. That is what we call true positive, right. There is something called true negative. For instance, where model predicts that absence of a condition of a fire, right, and the truth is also there is no fire, right. Or you can look at a medical test, it says negative for a patient who does not have the virus, right. So that is the instance that we are looking at as a true negative. There is something called false positive, a type 1 error occurring when the model incorrectly predicts the positive class for an instance that is actually negative. For example, in a security system, motion sensor is triggered by a stray cat, incorrectly signaling as an intruder, right? Or a false negative, right? False positive and false negative. False negative is a type 2 error occurring when the model incorrectly predicts the negative class for an instance that is actually positive. A metal detector failed to beep when a person walks through carrying a concealed weapon, right? Those are something which we need to understand. So if you look at it, I can create a confusion matrix where the actual ground truth, predicted one, actual is positive, prediction is positive, then this becomes true positive, the correct accept. Actual is negative, your prediction is also negative, then we have a true negative. But actual is negative, but you are predicting positive, then you led to false positive. Actual is positive, then prediction is negative, then you have false negative. With that, we just look at much more detailed understanding. What's your precision? True positive divided by sum of true positive plus false positive talks about precision. Recall is true positive divided by true positive plus false negative talks about recall. You can compute the accuracy also. Accuracy is nothing but true positive plus true negative divided by total number, right? So you can sum of all this. So in 2 class problem we can do. We can try to understand the accuracy. If you look about a same thing in an n class problem, the matrix is going to be n cross n, right? If all diagonals are equal to 1, then I can say the classifier is able to understand the relationship in all classes and come up with the decision surface which can segregate the classes as accurately as possible. The confusion matrix gives a lot more interesting insight into it. There could be samples similar. For example, if you wanted to differentiate between different types of cats, right, along with dogs, you can differentiate dog and cat very well, but subclasses of cat, there could be an overlap. There could be some of similarity. We can try to understand when you are looking at false positive and false negative there, what's really happening, right? What is making it difficult to separate those subclasses, right? That will give a detailed understanding about why the network is not able to segregate the subclasses accurately or not. What is required? We may need more samples to understand the relationship. We will be able to figure out by looking at the confusion matrix, right? Just to give you a summary of definition in terms of what is accuracy, and there is an interesting aspect we bring in what we call F1 score. It talks about harmonic mean of precision and recall. We defined what is precision in the previous slide. Precision is nothing but true positive divided by true positive plus false positive. Recall is true positive divided by true positive and false negative. The F1 is nothing but 2 times precision into recall divided by precision plus recall, right? It just gives you a harmonic mean of these two, right? So we use different metrics at a different point of time to really understand why the network is able to capture the not able to capture the relationship between input and output, right? What is happening? Is the learning is a problem, or is the data is a problem, or data presentation is an issue? So we can understand. So we need some metrics to evaluate, right? This gives end of this particular lecture. This gives you an understanding about what are the different learning paradigm we have: supervised learning, unsupervised learning, semi-supervised learning. Again, in unsupervised you can talk about reinforcement learning too, right, where there is a feedback signal but that's not exactly the feedback signal, right? And we talked about data preparations, sample space. How do you represent the sample space? If the sample space is not capturing the true distribution, again you will have a bias that will lead to poor model which will not generalize better. Not just the data, your data is uniformly distributed, but still the data preparation is important, right? You want to get zero centered, normalized so that all features are given equal importance to get the relationship, right? How do we know my learning is effective or not? We have to look at the evaluation matrices, right? For prediction, different evaluation matrix, and classification, there are different evaluation matrices. These matrices will give some insight into the learning process, right? Sometime what will happen, the learning may be overtrained, right? Or your network is not sufficient to capture the relation. So you need to understand all of this. In subsequent lectures, when we go on to this module, we talk about how the activation function, why activation function and the data normalizations are connected and what will be the effect of it, how to present the data, how long you present the data so that we can learn it more effectively, when we should stop learning. These are the questions very important when you work on learning based system. We will discuss those in subsequent lectures. Thank you.